Almost everything in our modern world, from the medicines we take to the materials that protect us, is held together by microscopic carbon-carbon bonds. But carbon atoms are notoriously difficult to manipulate. These bonds are incredibly strong, making it a constant struggle for chemists to break them apart or move them into new configurations. For over a century, building complex molecules was a messy, brute force process. Scientists often had to run a material through dozens of individual chemical steps just to link a handful of carbon atoms in the correct order. This traditional method is highly inefficient. Every step in the process creates toxic byproducts and raises the cost of manufacturing to extreme levels. To create the advanced technologies of the future, researchers needed a different approach, a way to snap carbon molecules apart and reconnect them with surgical precision. In the 1950s, industrial engineers observed a reaction they couldn't explain. While working with metals and carbon compounds, they saw molecules suddenly scramble and reorganize themselves, a phenomenon they eventually named Olefin metathesis. The reaction remained a mystery until 1971, when a French chemist, Yves Chauvin, published a mechanism that mapped out exactly how these atoms were rearranging themselves. Chauvin realized that a specific metal catalyst could act like a dance collar. It forces two carbon molecules to break their strong double bonds, at which point each carbon atom swaps partners. This reversible swap creates entirely new molecular combinations that were previously considered impossible to assemble in a single step. Chauvin's theory proved that a perfect molecular cut and paste was possible. The next challenge was to build a physical catalyst that could survive outside of a highly controlled environment. This proved difficult. Early attempts to build the necessary catalysts resulted in compounds that would degrade or catch fire the moment they were exposed to normal air and water. In 1990, American chemist Richard Schrock made a significant breakthrough by creating the first highly active metathesis catalyst using the metal molybdenum. While Schrock's catalyst was incredibly fast and efficient, it was still extremely fragile. It remained highly sensitive to environmental moisture and required very careful handling. Robert Grubbs moved the field forward by engineering a different version of the catalyst using the metal ruthenium. The ruthenium catalyst was a major shift in practicality. It was so stable that chemists could finally use it to build molecules on a normal, open-air laboratory workbench. By refining Chauvin's theoretical blueprint into a physical tool, Schrock and Grubbs gave the scientific community a reliable way to manufacture complex organic structures. With these stable catalysts, organic synthesis became as predictable as snapping together Lego bricks. The pharmaceutical industry now uses metathesis to rapidly produce 400-kilogram batches of life-saving drugs, dramatically reducing the time it takes to get medicine from the lab to the patient. Metathesis is also used to trigger the creation of ultra-durable polymers. These are found in consumer goods ranging from bathroom fixtures to high-performance composite baseball bats. Because these metathesis-derived polymers are so strong and lightweight, they are even being used to manufacture advanced ballistic panels for body armor. The reach of metathesis extends far beyond the laboratory, providing the foundation for a new era of physical manufacturing and materials science. This method is also a cornerstone of green chemistry. By reducing the number of steps required to build a molecule, metathesis eliminates the generation of toxic waste and chemical runoff. In agriculture today, scientists are using metathesis to convert inexpensive, renewable seed oils into highly targeted insect pheromones. These pheromones protect crops by confusing pests, providing an effective way to manage insects without the use of broad-spectrum pesticides. By learning to swap microscopic carbon fragments with such precision, Chauvin, Schrock, and Grubbs provided the tools to build a cleaner, more resilient world.